Hey, welcome to a new POPX tutorial. Today we're growing neural paths through a 3D head with the shortest path solver, watching them branch, grow, and dissolve. Let's dive in. Reference. Before we start building, a quick word about where this one comes from. This whole tutorial is inspired by Konstantin Magnus, a Houdini developer and artist. A while ago, while developing POPX, I came across his YouTube channel. I'm not a Houdini user myself, but I take a lot of inspiration from Houdini developers and artists converting their work and figuring out how to do it in real time with TouchDesigner. His shortest path tutorial is the one that inspired me to develop my own shortest path solver, which eventually made it into the latest version of POPX. So I really recommend checking out his channel and his free tutorials. If you're a TouchDesigner or GLSL coder, his simulations and techniques are full of ideas worth bringing into real time. Alright, let's get building. Overview. In this build, we're using the POPX Shortest Path simulation. It works like a pathfinder. Give it a field of points with a start group and an end group, and it traces the shortest route between them, creating line strips that connect the points into paths. Here, we grow those paths through a 3D head, then loop the animation so they bloom and dissolve over time. The network breaks down into 4 parts. First, the path geometry. This is where we build the points we'll feed into the shortest path solver. We start with a file in, bringing in our head mesh. The mesh is really just a boundary. It defines the space the paths are allowed to fill. A sprinkle pop scatters points all through the volume of that mesh. The solver can only travel between points, so this cloud becomes the stepping stones our paths hop across. But we don't want paths cutting straight through the center where the brain would sit. So a spherical shape fall-off marks out that region. We delete those points, and with no stepping stones in the middle, the paths are forced to wrap around it. That's what gives them their organic, branching shape. Then 2 group pops define the endpoints, because the solver needs to know where every path starts and where it's allowed to finish. The start group sits at the base of the neck, so all the paths share one common route. And the end group picks points at random, up through the head, so the paths fan out in every direction. Second, the shortest path. The solver connects our scattered points into line strip paths. We set neighbors to by distance, not connected, because our points are a loose cloud with no topology, so the solver has to link each one to its nearest neighbors instead of following edges. Straight out of the solver, the routes are jagged, hopping point to point, so a line smooth relaxes them into flowing curves. Third, the sweep. A POPX sweep wraps each path into a rounded tube. A line strip has no thickness and won't catch light, so the sweep gives it real surface to shade and render. A ramp drives color along the curve, so each path reads with its own gradient. And a second ramp drives scale along the curve, tapering the ends down to nothing. That's what makes the paths appear to grow in and dissolve away over time. And finally, rendering. A PBR material, a camera, and 2 lights, 1 point light and an environment light to give the tubes depth and shape. A render top renders the whole scene. After it, an anti-aliasing top cleans up the edges. Then a Luma blur top, driven by a circular ramp top, blurs the edges for a depth of field effect. And a level top lifts the brightness to finish the look. Alright, let's get started. Hey, before we dive in, I want to show you popx.tools, the official POPX website. Here you'll find a Getting Started page with some basic examples. An installation guide. Comprehensive documentation for every operator. And a changelog for each version. Everything else lives on Patreon. That's where you get POPX itself, all the releases, the tutorials, and the project files. The links for the website and Patreon are in the description. All right, let's get into building it. Path geometry. Let's build the path geometry, the points the solver will run through. We start with a file in POP and point its geometry file path at the head model from the project folder. Connect that into a sprinkle pop and set the method to volume so it fills the inside of the head with points. Push the point count up to 200,000 for plenty of detail. If you're on an NVIDIA RTX card, switch the hardware ray tracing over to fast build dynamic geometry. It scatters all those points much faster. And changing the seed gives you a different scatter and different paths later on. Next, we carve out the middle of the head where the brain would sit so the paths don't run straight through it. Connect the sprinkle into a shape fall-off and turn on the fall-off preview so you can see exactly what you're selecting. Set the shape to a sphere with radius x at 0.25, radius y at 0.2, and radius z at 0.25. Then, on the transform page, translate it up on Y by 0.2 so it sits right where the brain would be. Feel free to tweak the size and position to taste. Now a delete pop clears those center points out. On its attribute page, pick the POPX falloff attribute that the shape falloff just generated. Set the function to bigger than with a value of 0.5. Everything inside the sphere scored a 1, so this deletes it, leaving the brain region empty. Back on the shape fall off, you can switch the preview off now. We don't need it anymore. With the points shaped, we tell the solver where the paths begin and end using 2 group pops. Connect the delete into a group pop and name the group Start. Toggle on the debug color so you can see the selection. Chosen points show white, the rest stay gray. On the attribute page, choose P1, the position on the y-axis, because we want the very bottom of the neck. Leave the function on smaller than and set the value to -0.45. That tags the points at the base of the neck as our start group. Then a second group pop, fed from the first, named End. Turn the debug color off on the first one and on for this second one. On its thin page, turn on Enabled. This picks the endpoints at random. Set the thin steps to 2, the thin random to 0.125, and the random seed to 6. Tweak these for a different spread of paths. Then toggle the debug color back off so we hand clean points to the solver. Finally, cap it with a null pop and name it Path Geometry. And that's our geometry, ready for the shortest path solve. Shortest path. Now let's solve the shortest paths. Drop in a POPX shortest path and connect our path geometry into its first input. To see what's happening, split the view and set the right pane to a geometry viewer, then turn on the display flag on the shortest path. Nothing shows up yet because we still need to set its parameters. First, the point groups. Type start for the start group and end for the end group, the two we made earlier. Set the neighbor type to by distance, not connected. Our points are a loose cloud, so there are no connections for it to follow. Now for any paths to actually appear, we have to raise a couple of limits. Push the max number of paths up to 100,000 and the max vertices per path up to 500,000. And right away, some of the line strips appear, though only across half the head so far. That's the max neighbor distance. It's too small at 0.1, so bring it up to about 3. Then push the number of hash buckets right up around 2,000, which helps it connect across the whole cloud. And bump the max neighbors up to 15. The solver is iterative, so the more iterations, the more paths it finds. Around 200 works well here. Now we've got the full set of paths the solver can find. Grab the first output, the line strip paths, and feed it into a line smooth pop. Turn the display flag off on the shortest path and on for the line smooth so we can watch it work. On the line smooth, turn on endpoints fix so the ends stay locked in place while the rest relaxes. Then set the edge distance to 0.85 and the effect, the amount of smoothing, to around 0.6. Tweak it to taste for your own look. And that's the shortest path network. Our paths are solved and smoothed. Sweep. Now for the sweep. Our paths are still bare line strips, and a line with no surface can't catch shadows or light, so let's wrap them in real geometry. Drop in a POPX sweep and connect it after the line smooth. Toggle the display flag off on the line smooth and on for the sweep so we can see the result. The lines have thickness now, but it looks wrong. Everything is skinned together. We just need to set a few parameters. On the Orient Curve page, the defaults are fine. Reorient Curve is on, computing each line strip's orientation with parallel transport, exactly what we need. You could add twist here too, but we'll skip it. On the surface page, the skin parameter defaults to all primitives, which connects everything into one surface. Switch it to per line strip so each path is detected and skinned on its own. Set the width parameter down to 0.003 for thinner strands. Columns is the number of sides on each tube. 8 is the default, around 6 still looks good, and fewer columns keeps the render lighter. Output quads is on by default. You can toggle it off to output triangles instead, which is sometimes better. Now we want the paths to grow in from their roots, so let's animate scale along the curve. Toggle on Apply Scale along curve. By default, it uses the built-in ramp editor, but we want this animated, so we'll drive it with a custom scale top. Let's build a small system for it. Start with an LFO chop as the driver, keep the type on sine, set the frequency parameter to 0.05 for a slow wave, and the phase to 0.25, so it starts at 1. Connect it into a math chop. On the range page, set the from range to -1 and 1, the sine wave's natural range, and the to range to -1 and 0.05. Cap it with a null chop named TX. This will drive the ramp's translation on the x-axis. Drop a keyboard in chop next to the LFO and reference its key one channel onto the LFO's reset parameter, so pressing 1 restarts the animation. Now the ramp. Drop a ramp top and on the common page, raise the resolution to 1024 by 1024 and set the pixel format to 32-bit float RGBA. We want it mostly black, with just a thin white stripe on the right. Add a new key, set it to black, and drag it as far right as it will go. After the ramp, add a transform top. Reference the TX channel from our null onto translate X, and on the tile page, set the extend to hold. Press 1 to reset, and watch the texture. A wide stripe sweeps from right to left, covers the black, then falls back out. That's the ramp driving our growth. We never want the width hitting exactly 0. That causes render artifacts. Add a limit top, set both limit types, minimum and maximum, to clamp, then set the minimum value to 0.001 and the maximum to 1. Connect the limit into another ramp top. On its output page, the operation is already multiply, which is what we want. It keeps the roots of each line thick, thinning out toward the tips. On that ramp's black key, raise the value to around 0.4 so the tips never get razor thin. Cap the chain with a null top called scale ramp. Then on the sweep, reference it into the custom scale top parameter. And there's the growth, paths sweeping in and out, with the roots thicker than the tips. Time for color. Create another ramp top with the same setup, 1024 by 1024, 32-bit float RGBA. Pick any colors you like. I'm copying the ramp from the example file. To keep the colors drifting, the phase parameter is animated with the expression -abstime.seconds times 0.2 with the period at 0.5 and extend left set to mirror. Cap it with a null top called color ramp. On the sweep, toggle on apply color along curve and reference the null into the custom color top parameter. One more fix. Because we clamped the scale above 0, tiny slivers remain where the paths should have vanished. Drop a multiply top, color ramp into the first input, scale ramp into the second, and connect the multiply into the color ramp null. The slivers turn black and disappear from the render. If the tips pick up some unwanted black, add a threshold top between the scale ramp and the multiply, set the threshold value to 0.001 and the darkness is gone. Last, the output. Connect the sweep into a null pop and the null into a geo comp. Toggle the display flag off on the sweep, the geo shows it from here. And that's the sweep network. The paths are real surfaces now, growing in, tapering, and shifting color. Next up, the rendering. By the way, if you don't want to build the network from scratch, you can grab the project file from Patreon, along with the project file for every tutorial I made. The link's in the description. Alright, back to building. Rendering. Last up, the rendering. I'm not building this one from scratch. The render network is copied straight from the example file, so let's walk through it. First, so we can watch the final image, set the right pane from Geometry Viewer to Panel. Here's why that works. On the path bar, right-click Project 1, our project container, and open its parameters. On the look page, the background top parameter references the out1 top at the end of the chain, so the panel shows the finished render. We've got a PBR material here with a few tweaks. Base color raised, metallic lowered, and a touch of roughness. Reference it on the Geo's material parameter, so the paths pick it up. On the Geo's Xform page, let's slowly spin the head. On the rotate parameter, set Y to the expression abstime.seconds multiplied by 10 so we see the growth from every angle. The render setup itself is simple. The render top references our geometry, the camera, and the lights, with anti-aliasing on and the resolution and pixel format set. Lighting is just two lights, a point light with soft shadows and an environment light dimmed way down, around 0.1 on the dimmer, sampling a simple texture from the TouchDesigner samples as the NV map. After the render comes a second anti-alias top. These thin strands get noisy, and the extra pass cleans them up. Then a circular ramp top drives a luma blur, softening the edges of the frame for a bit of a depth of field feel. And last, a level top. Boost the brightness, raise the gamma a touch, and tweak the grade to taste. And that's it. The Procedural Neural Paths network is complete. Thanks for following along. Thanks for watching, and huge thanks for the support. That's what keeps POPX evolving and the community growing. Come hang out on our Discord to ask questions, share ideas, or just chat with other creators. The links to the project file and Discord are in the description. See you in the next one.